Okay, onwards. What is vaporization? So try to think of an example of vaporization. Oops, evaporation, it's right there. Okay, so boiling is one kind and evaporation is another. Okay, they're both considered a transition from the liquid to the gaseous state. In order to vaporize, liquid particles must have enough blank to overcome blank. So we just kind of alluded to this in a couple slides ago, so go ahead and take a second and try to fill that in. Okay, enough kinetic energy to overcome IMFs. Okay, so if you think about, let's go back to this curve that we drew before. This one that we'll come back to over and over and over again. And you can, this is a good time for you to practice the shape. Whoops, that's not a very good one. Okay, so that's not great either, it doesn't matter. Okay, so remember that this represents the number of particles in a particular sample that have a specific amount of kinetic energy. Okay, so like some particles, not that many, have this much, a high amount of kinetic energy, right? And some have a small amount of kinetic energy, and a lot have the average amount, right? So, okay. In any sample, you have some particles that have a substantial amount of kinetic energy up here, right? And this kind of goes off. So if you sweat, for example, your sweat is obviously not 100 degrees Celsius, like it's not boiling, or that would be really problematic on a lot of levels. But still, some of it evaporates. And even if you have water sitting on a table, it'll eventually evaporate. So which particles are evaporating? It's the ones in the sample that have above average kinetic energy. So this whole group up here at the top end, we would say the particles with the most kinetic energy are the ones that will, particles with the most kinetic energy can evaporate because they have enough kinetic energy to overcome the intermolecular forces, which is what we wrote up there. Okay, so there's like a minimum amount of energy that you have to have. We would say this is like the threshold minimum kinetic energy to evaporate. Okay. And so we would say those with above average kinetic energy. I mean, not just above average, like maybe we should say it the most. Oh, I've got someone leaving this room. Okay. So how does evaporation cool? Well, if you think about it, if you, for example, take all of these particles that are left behind that don't include the ones that left, and you find the average of these particles, the average of these will be maybe down here because you have taken out the highest ones. So maybe the average, okay, so the blue shows the average kinetic energy before the highest energy ones evaporated, and then the red shows the sample after those are gone, and now there's a lower average. Okay, do we see that? So this would be, for example, if the average on a test was an 85, and then I threw out the 3 highest grades, the average might go down to an 83 or something. So it's a similar idea. So the average kinetic energy dictates the temperature, like they're directly related. So with a lower average kinetic energy, you necessarily have a sample with a lower temperature. Okay, so removing, you can phrase it however you want. Maybe I'll let you phrase it to yourself while I write it, and then you can compare what I wrote afterwards. Okay, so just to read that in case you can't read it, removing the particles with the highest kinetic energy lowers the removing the particles with the highest kinetic energy lowers the average kinetic energy of the remaining particles, which lowers their temp, which lowers the temp of the particles remaining. Okay, why does evaporation happen faster at higher temperatures? Okay, so I'm going to draw one more of those graphs here. Okay, and we have a curve again, And we have this like minimum energy, right? And we'll say minimum kinetic energy to evaporate. And then we'll say at this temperature, this many particles were able to evaporate. Okay, what if, and let's say that this was 50 degrees Celsius. Okay, what if we get to a point where we have, it's hotter, I'm gonna make it green just so it's not confused with that other one, even though green doesn't seem hotter. Okay, so if you do something like this, okay, that's pretty good. Okay, now we see that in this sample, at this higher temp, a substantially greater portion of the sample has enough kinetic energy to evaporate. Okay, maybe this is closer to boiling. Okay, so you would see that at higher temperatures, a greater portion of the sample has enough kinetic energy to evaporate. Or we could say has the minimum kinetic energy to evaporate. Okay, so the last thing we're going to talk about here is vapor pressure, and then we're going to do a demo. So vapor pressure, so let's say you have this completely empty container flask here, and you put some liquid in the bottom. Of course, it's not going to be empty because you're going to have like the air will get in there, and that's always bouncing around off the walls, right? But we're ignoring that for now. So you add some liquid, and some of those particles are the ones that are up here with more kinetic energy, right? Those ones evaporate and start bouncing around in the container, okay? And as you accumulate them up here, some of them also collide with the water and end up coming back down. So initially you have this process where a bunch of the liquid is becoming gaseous, but if you accumulate enough, now you have equal amounts condensing and forming liquid as you have evaporating and forming gas. So at some point, the total amount of particles here that are gases will be constant. We'll call it a constant amount in gas form eventually, right? I'm going to write eventually. That doesn't happen immediately. It has to get up to that. And when you're at that point, you're at what's called dynamic equilibrium. The rate of evaporation is now matching the rate of condensation. And at that point, these particles are exerting a certain pressure on the walls of this container, and we call that the, sissy, and we call that the vapor pressure, okay? So, liquids that evaporate rapidly have high vapor pressures, and we call them, this is a word that means, like, you can describe a person as, oh, I almost said it. You can describe a person as this. It means that they are, like, not a very stable, they kind of, like, are all over the place emotionally. Anyways, that word is volatile. So a liquid can be that, too. If you have a volatile liquid and you leave it sitting out, it just evaporates. Like, it is really unstable. Okay? So what do you think would determine how high or low the vapor pressure will be for a particular liquid? Like, why do you think some liquids, it might be easier for them to evaporate? And if we go back to this graph one more time, and then we'll do our demo. Let's say you have two liquids. Let's say you have two liquids at 25 degrees Celsius. So they're going to have the same curve here, right? Because they have the same temperature. But let's say that one is more volatile than the other. We won't give them identities yet. Okay, so let's say that one of them, this much energy is required to evaporate. Okay, so this many particles can do it. This is just what we talked about before. Let's say the other one, only this much energy is required to evaporate. Why would one require less kinetic energy to evaporate? If we go back up here, in order to vaporize, liquid particles must have enough kinetic energy to overcome IMFs. Okay, so if something evaporates more easily, like less energy is required to evaporate, that must be because it has weaker IMFs. That's a bad color to pick, isn't it? Okay. Okay, whatever. All right, so we can see that for these ones, a greater amount would evaporate. And in this case, it would add even more vapor pressure in here, right? Because less was required to do that. Okay, so how do we measure it? Okay, now you're going to see this introduction to this demo. It's going to explain how this piece of equipment works, and it's a piece of equipment that measures vapor pressure. And then I'm going to ask you guys a couple questions